All right, so as we continue on the notes here, so we took a look at the introduction to applied max and min problems, that's optimization in calculus. We did example 1, went through all the steps for optimization. That was in part 1. And now we're looking at a few examples. So here we go, example 2. If 2,700 centimeters squared of material is available to make a box with a square base and an open top, find the largest possible volume of the box. Okay, so what I would do is I would take a moment to sketch the situation if possible. It doesn't have to be a perfect sketch, but here I've sketched a box that has an open top, so I can kind of see what's going on. A net of this would be really helpful as well. You see that you have a bottom of x by x, right? And then you have 4 flaps, really, and these are x by h. Right? So that's sort of, that's what it looks like if the box was flattened out. So you have x squared. So the material itself, let's start with that. The material itself is 2,700. So this is not going to be the equation that we're going to optimize, but this is part of the given information. So 2,700 has got to equal all of the surface area of the sides of the box. So that's going to be x squared plus 4 times x times h. That's the area of the rectangles on the side. Okay, how does that look? Does that look good? Okay, so this is the extra given information. What we're actually trying to optimize, I'll put that in red, the largest possible volume of the box. So the volume of the box over here is going to be, well, it's going to be x squared times h, right? It's length times width times height. That's the volume of a box. Good? All right. So the volume is what we want to optimize. So the largest possible volume, that is those are the words that you're looking for. That's optimizing, okay? So we're trying to optimize volume, find the largest volume. So this is what we want to do the calculus on. And please remember, I've had lots of students in the past kind of get into this and forget to do calculus. We have to remember to take the derivative later. There's a lot of steps, and honestly, sometimes kids just forget the taking the derivative part. So this is what we're going to do the calculus on. Okay, we're going to find the derivative of this. But if we look back to our rules here and set up. Okay, so we've set up the relation. Actually, let me just copy this for you. So we've set up a relation of what we want to optimize. And the second point was write the relation of the function in terms of only one variable. So that's where we use our second bit of information. And you see we have an x and an h in the volume. It's not a function of just one variable yet, so we have to substitute something. So it's tough to solve for h here because it's in 2 different terms, but it's easy to solve for h. Sorry, did I say? It's tough to solve for x because it's in 2 different terms, so we're going to solve for h. So this is going to be 2,700 minus x squared equals 4xh. And then we're going to divide by 4x. So we're going to have h equals 2,700 minus x squared over 4h. Over 4x, thank you. All right, can we simplify that? Well, we can write it in 2 separate terms, I suppose, but it's probably not going to help us because we're multiplying. So let's just substitute h here now. So we're going to have, this is solely going to be in terms of x here now. That's great. So x squared, we're going to times 2,700 minus x squared over 4x. And now that is indeed all in terms of x. We have a function of volume as a function of x only. That's easy for us to do calculus on now. And remember, the goal of this is to find out where our critical numbers are. So because at critical numbers are where a potential local maximum or minimum is going to be. So if we're going to find a local maximum here, I want to find out what the critical numbers are. So I need to take the derivative of this function. But before you go ahead and do the derivative on this as it stands right now, please notice you can go ahead and take the derivative now, but you're going to be dealing with a product rule and a quotient rule. Okay? And many times it would be a good idea to simplify your expression before you do calculus. Because with this one, if you multiply x squared in and then simplify one rational, you're going to be able to whittle this down to something a lot more manageable. It's going to be easier to take the derivative of. So that's what I would suggest. So you could actually, I mean, that might be part of the steps really, is to simplify the expression before taking the derivative. So what I mean by that is I'm going to multiply this in. It's going to be, actually, we could just kind of go ahead and cancel an x here and an x on the bottom. We could do that. So this squared would go with this x, right? They would divide out. And then I'm going to have 2700 x minus x cubed. And then that's going to be over 4 still. Over 4. Because we still have a 4 there. All right. Now, we still have a fraction, but can we simplify this a bit? Well, we could, I guess. We could do 2700 divided by 4 and maybe try and whittle that down a little bit. That's not going to be too friendly, but we could probably do that. You could take that 1/4 and put it out front, like so. So we could do this, 1/4 times 2700 x minus x cubed. Now, why might I do that? Well, in your derivative rules, if you have a constant in front, you can just leave that constant out front and then take the derivative of, this part right here. So this is like a scalar. It's just like a constant in front. So, whatever you want to do. You could write this as 2 terms. You could write this as 2700x over 4 minus x cubed over 4. You could do it that way and take the derivative of each term and so on. Or you could do it this way. So I don't know what's going to be easiest for you or what you like better. But let's try this one so I can show you how this works. Okay, so now we'll take the derivative. So don't forget to take the derivative here. So we've done a lot of work already, haven't even touched any calculus stuff yet. So I'm going to leave this 1/4 alone, and I'm just going to take the derivative of this right here, which is going to be 2700 minus 3x squared. So that's great. Now we have the derivative here. Now I can let this equal to 0, right? Identify critical numbers. So in step 4, I want to let this equal to 0. So this is my derivative. I'm going to let that equal 0. I'm going to multiply both sides by 4, and 4 times 0 is, shockingly, still 0. So that constant really didn't matter too much, eh? I'm going to get 3x squared over this side. I'm going to divide both sides by 3. And I'm going to get x equals 30 here, it looks like. Now, does that look good? 700, 900, 30. Okay. So let's just go see, let's see if this might be a reasonable critical number here. So I got 2,700 centimeters. Okay, so 30 times something might give us 30, yeah. Well, do we have? Let's see. I don't know about that. Should it be? Minus 4x. So if x equals 30, then what I have to do here, so I have to find the largest possible volume. So I've got x equals 30. Yeah, that looks pretty good. I have to find out what h is now. Okay, and simply I do have h solved for here. So 2700 minus x squared over 4x. So h is 2700 minus 4x squared over, or just x squared, I should say. And then you just go ahead and solve for h there, plugging your x equals 30 in. So 30 squared is 900, and 4 times 30 is 12. Sorry, 4 times 30 is, just is 120. So h equals 7 minus 900, so 1800 over 120. So h equals 15. Now, if x is 30, h is 15, that everything should line up with the materials. So 30 times 15 should equal 2700. And these are the dimensions that are going to give us the largest possible volume. So find the largest possible volume. So with these values, I want to go back now to, my original volume, one of my original volume equations. So you can pick any one. We have h, you could have used this one too. So x squared h, they'll both be the same. This one's maybe a little bit more complicated, but here we go. There's the other one too. So just 30 squared times 15 is your volume. So what do we get there? So we get 13,500, and make sure you include your units as well. Yeah, so either way, you have both x and y, so you could go with this one here. This actually isn't volume as a function of x, really. That was had the y, or had the h in it, but either one. So there's your answer. Maximum volume of the box. Questions? We're good? Okay, let's do the next one then. So find two numbers whose difference is 150 and whose product is a minimum. So we want to minimize the product, right? So I usually do what we're trying to optimize first. So product is, and we got just two numbers, so x and y. Now I made a little note here that x is going to be the larger and y is the smaller. Why? Because the difference is 150. So the secondary information is always going to be two bits of information, something that you have to optimize and something that gives you sort of the parameters for the variables. So x minus y equals 150. The difference between the larger and the smaller is 150. Okay. Now, I want to minimize the product, and so I need that just in terms of one variable only. So I'm going to go back over here, and I usually like solving for y because I like x as my input variable. It's usually what happens. So x minus 150 equals y. That's how this simplifies over here. So I go back to my product function. This is going to be p of x now. I only have x in there, and I have x times my y is x minus 150. I'm going to simplify my p of x because I don't want to do product rule. So I'm going to multiply this x in. It's going to be x squared minus 150x. Sound good? This is fine. I'm going to take my derivative now. So the derivative, p prime of x, is going to be 2x minus 150. So that's the expression for the slope of the tangent line, and I want to find out where the slope of that tangent line is 0, because that's where either a maximum or a minimum is going to be. So let this equal 0. To find the x value that is associated with this critical number, x equals, looks like 75. So if x is 75, that means that y equals 75 minus 150. Y is negative 75. Does that seem reasonable with the question? Find two numbers whose difference is 150 and whose product is a minimum. Sneaky. There is 150 between negative 75 and positive 75. And because one of them is a negative, that's going to make for a very small, technically, negative, right, product. Okay, so that's pretty tricky. So it looks like this one's going to work. So find two numbers whose product is a minimum. So the two numbers are 75 and negative 75. It does not ask for the product, but we could easily find that too if necessary. Now you won't have graphing technology for you should be able to do this algebraically like we're doing. But if you are doing your homework and you're studying and you don't know if you have the right answer or not, what you could do is you could graph this function wherever, one of these two, graph your original function just in terms of x, and I'll take a moment to do this with you. And then you should have, this is a parabola that opens upward, right? You see, it's a parabola that opens upward, so there should be a minimum point there, and that should be at x equals 75. So let's pop over to Desmos and check that out. All right, so here's the graph. The lowest point here, look at that. The vertex there is 75 with a product of negative 5,625. So there's your x value, 75. So that does check out. Okay, find two numbers whose difference is 150. Product is the minimum. The x value for this that we found here was 75. Okay. All right, why don't you guys try this on your own? Yeah, they're in the top drawer. So I have two more here. Why don't you guys do number 2, because it's very similar to this one, and then we'll do number 3 together with you hopefully before the end of class here. All right, so what we're trying to do is to find two positive numbers with a product of 200. So product of 200. All right, such that the sum of one number and twice the second is as small as possible. So small as possible, that's what we're trying to optimize right here. Okay, the sum. So I have sum is one number plus twice the second. And I also have that extra information over here of the product of the two is 200. Excuse me. So y is going to be 200 over x. And I can plug 200 over x in for y over here, and I get a function of x. Do a little simplification. I have s of x equals x plus 400 over x. Take the derivative. Derivative of x is 1. Derivative of 400 over x is negative 400 over x squared. Let that equal to 0. Solve for x. You get plus or minus 20. And of course, there's two positive integers we're looking for. So x is going to be 20. You use x to find y. So you go back to this equation right here. And you plug 20 into there. And you get y equals 10. And so the two numbers are 20 and 10. And the sum, no, it doesn't ask for the sum. Find such that the sum. So if you wanted to find the sum here, if you were asked to find the sum, you could do that. You could do 20 plus 2 times 10 is 40. Now, it just says one number and twice the second. So, yeah, the two numbers are 20 and 10. You could have two different sums, though, if you switch the numbers around. That's what I'm showing here. So the smallest would be 40. Here, you could 50 if you put the other one in, I guess. Does that make sense? 20 and 10. Anyway, so the two numbers are 20 and 10. All right, so a rectangle is a perimeter of 100. This is question number 3. So we have a rectangle over here. The perimeter, if this was x and y, 2x plus 2y is 100. Okay, so that's some information that's given. What we're trying to optimize is what length and width should it have. So that's just saying what are the dimensions, x and y. So x equals what? Y equals a crashed program. Y equals, oh, it didn't. That's pretty cool. Should it have to have a maximum area? Awesome. So area is xy. Now I want to solve for y over here, so I'm going to do this. I'm going to do 100 minus 2x, and then y equals 50 minus x. Does that make sense? So the area now, as a function of x, is going to be x times 50 minus x. I'm going to simplify this because I don't want to do product rule so much. I just want to do power rule, so I'm going to do this. Now I'm going to take derivative. 50 minus 2x. I'm going to let that derivative equal 0. 2x equals 50. X is 25. All right, I'm going pretty quick here, so you don't have to go this quick yet, but hopefully you'll be following along here. So if x is 25, that means that this is our critical number, and we're looking for a maximum area. So y then is going to be, so 2 times, or sorry, y is going to be 50 minus 25, or 25 as well. So the dimensions should be 25 centimeters by 25 centimeters. And just to check that, is that really a maximum area? Well, if you took a really skinny rectangle, right? That's like a perimeter. So this is like 40, should say 40, and 10. So 40 times 10 is 400, right? As an area. 25 times 25 is 625. So this is definitely larger than one other example I can think of that would fit. And so it's reasonable that this is a maximum. Okay? All right. Now your 4.4 assignment from your text is right here. So take a moment to copy that down. It's also on the website. Here it is right here, 14. So there's your chapter 4 homework here so far. We are going to have a optimization assignment you're going to be starting this week as well. So.